Essentially, yeah, I think so. And then yeah.
Wait, is that the actual equation or is that just your approximation?
That's the equation that he wrote on the board, so let's just keep it. This is section 12.8, by the way.
But this is 12.8?
Yeah, 12.8.
1
This
second.
and also the resonant frequency, this equation.
Yeah, section 12.8.
Yeah, we need these two equations. I know that for sure.
Hold on.
Let me actually write the FR a little more neat.
Oh, I found it in...
So ABC is like the dimensions, if I recall correctly, of like your waveguide. So like you have A, B, and C. And then your M and P is that supposed to be like, those are just like your, like, remember we had like the TE, like 1-0 modes, all that stuff. So I think that's like these.
I don't fully understand. 1 second. So you said A, B, and C were dimensions?
Yeah. Best way to make sure though, I'll check the homework. Let's see.
Okay. All right then. So
You know, I was kind of blindly doing the homework without understanding what was happening.
Oh yeah, so A and B, those are ABC, those are going to be your dimensions.
A, B, C, those are the dimensions.
And then what did M and P mean?
Those are just like different modes. So like for TE, like 0, 1. So like your M would be 0, your N would be 1, and then you would just plug it in and see what you get out of that.
Oh, one thing I didn't understand about the modes is freaking how do they work? Like what do you know? How do you know which mode you can and can't use? Because I remember some of the things were saying, oh, you can't use that one because it's like this or something.
Okay. Let's see. I remember here. So for TM modes, for transverse magnetic, M and N cannot be 0. So
okay, TM, M, and N cannot be equal to 0.
Yeah,
that's
so
transverse
no
magnetic, right?
Yes. And then for
wait, would you say no square waves?
Square waves?
Is that what you said? No square waves or?
No.
Okay.
I just said no MN. Yeah.
Okay, sounds good.
And then for transverse electric, M and N can be 0, but not simultaneously. So like you could have M equal 1 while N is 0, and you could have N equal 1 while M is 0, but you can't have both M0 and N0. This is no, and this is yes and yes. For the TE case.
Okay, in 10 seconds, you just explained to me what I was so confused about for this entire assignment.
I saw it like in the book somewhere. It's like it's in 12.8, or I don't remember exactly where it is. So it's somewhere in chapter 12. Like when they were like proving the like formulas for it, they just said like, hey, so when you have magnetic, it can't be this or that. So I don't know.
Yeah, no,
Martin, does the video that you're recording have audio? Okay. Oh, for sure then. Appreciate it. All right, awesome. All right, cool. Then well, I guess we should start studying from chapter 7 then.
Yeah, let's go at it for that. And then just from the load, like this is like 12.52. Like I think that's our best bet for that one because that's the only homework problem we got on it, and it's this formula, the resonant frequency.
Okay.
And he did mention he did put that on the board, right?
Yes, he did put that on the board.
Okay.
By the way, U prime is equal to 1 over mu epsilon. Square root, my bad, square root.
Those are both constants, right?
Yeah, those are constants.
Mu is like 4 pi times 10 to the negative 7th, right?
Mu naught, yes.
Oh, so mu naught equals 4 pi times 10 to the negative 7th. What does epsilon equal again?
Epsilon naught is 8.85 times 10 to the minus 12. Let's see. I just want to remember what U is. Yep, there
U
you
and
go.
epsilon are just like the constants times those, right?
Essentially, yeah. So like you're given, say, mu is equal to mu r times mu naught. So like in
And
silicon, I think it's like 1.2 mu naught. So like your mu r would be 1.2 for that.
okay.
Usually mu r is going to be just like some numbers, so don't worry about it.
I see.
Cool, thank you. And what about the EZS E naught sine m pi x over a sine n pi y over b, that type of thing?
That I have no idea. Let's see. It's probably gonna be for something in like 12 point. Let's see, what was it? Where was it? Where was it? Where was it? It was one of the problems. Oh, remember in 12.16 where we were given this essentially EI and we had to find HX. You see how it's kind of a similar format. You have a sine times a cosine times a sine or something like that.
Oh
Um,
no.
Oh,
I'm
okay, I see. Yeah. So
thinking,
basically, this was 12.16 problem.
yeah. I'm thinking he's gonna ask us find HY or something like that given this, and we'll just have to like convert it. I don't know. That's what I'm prepared for, if anything.
Okay.
So study
I'm
12.16.
I'd say study this whole homework. How's that?
That's probably a good idea.
Yeah, just do this entire homework. Like this
Yeah,
is
this is
all like
work.
chapter 11 and chapter 12 right here. That's gonna be on
Yeah.
there.
Well, okay, so I'm just going to read off what I have written in my notes because I was writing down exactly what he was saying basically for these problems. He said chapter 12 resonators given rectangular waveguides solved using separation of variables assumed for coefficient equation. So might ask about TN mode. Yeah, TM mode. Something about modes and resonant frequencies at which they exist and they don't exist at other frequencies. Be familiar with resonator derivations and properties. 12.8 section.
Yeah, 12.8 is literally problem 12.52. So you do that, you're good to go.
12.52. Okay.
Yeah, because 12.52 was the one where you have like this formula. You're given A, B, C, like the dimensions of your waveguide, and you have to plug in different values of M, N, and P, and you have to see like what resonant frequency is like under 50 megahertz or something like that.
Cool. Okay.
Yeah.
hmm
I have no
Oh,
idea what's going on.
That's okay.
Did you say something about problem 12.6? That being for that being
16. Wait, actually, let me
16.
check. Yeah.
Yeah, 16 is for that one.
I
That's
don't
the
understand
one.
what the mode is.
Oh, you don't understand what?
The TE mode.
TE
I
mode.
assume it's like something to do for just no, I forgot what it's for.
TE, you could read about it in 12.4, and TM, you can read about it in 12.3. They have their own derivations, but they're pretty similar. And then it's just basically when you're doing this for TM, like you can't just like you see how like in all these problems, like the only like 1001, 1001, like M and P, like
Yeah,
there's only TEs here. But then I have to have like for TM, you can't have zeros at all. So that's why like you'll never see like a zero. If you have a TM, you'll never see a zero in like the first two like spaces.
I see.
hmm
Yeah, that's
Oh, and
basic.
also, quick question.
Mhm.
So, for TM, you said it was 12 dot what? Which chapter or part?
TM
TE
is
12.4.
12.3
Okay, thank you.
for sure. See, I'll write that down. TM 12.3, and I think TE is in 12.4. Yes, it is. Yes.
Did he say he was gonna have chapter 13 on the exam too?
Yes.
Yeah, pretty antennas.
We're
Which
gonna
one?
Yeah.
base
13. Yeah.
It's like dipole.
13.7
13.7.
and
Okay.
13.3, 13.4.
13.3, 13.4, 13.7. Okay.
Yes.
I don't know why we're doing this. We haven't gone over it much, and I have no idea what's going on.
neither do I.
You know
Whatever
what
questions.
it's the professors trying to make themselves look good. That's what it is.
I think this test is gonna be heavily curved between the
Oh,
fact.
oh, absolutely. He don't even care about us learning that much. It's about how much he can get done. You see how much he was rushing through, like, let's see if I can get this done today. Let's see if I can get this done today. Rather than more focused on, like, are they even understanding this? The homework seemed good. I don't think they would cheat on this, obviously.
Well, no, I think that he's more just like not used to teaching this class, and he was kind of thrust into it last second, so he doesn't know the content too well, and it's not exactly his area of expertise.
Yeah.
Yeah,
So,
It's his first time teaching too, so like
mhm.
yeah.
I
I
think
feel
he'd be
like,
better. Like, go ahead.
however, there's a disconnect there, given that are they really understanding the material? Like that's the thing. Like I don't see no type of urgency of like maybe I can help him out a little bit more or whatnot. Or, I don't know. It's just I know nobody's like really giving it into him like explaining like here we need more help on this because we don't understand it. But he never really asked questions like how comfortable are y'all in this section? I don't think he ever asked that question once.
I mean, a lot of professors don't do that. I think.
Yeah,
Dr. Baker's the only one.
I understand it too. Yeah, he don't have that repertoire. I get it.
Mhm.
I was just thinking about like the student first, but I don't know. What do I know? I'm not a professor.
Okay, let's continue on then.
Yes, sir.
Yeah, let's do example 7.1. I think that's the best thing to do.
Did
So
he mention that was
what's
one of the
this?
ones? Yeah, okay, never mind. Sorry. Continue.
So what is example 7.1? We are going to be using the Bayard-Savart law. That's going to be fun. Okay. Yes. Yes, whatever you just said. And oh no, it's this guy again. Yeah. I remember how to use this.
That was just nasty.
Oh, no. Yeah, as you can see, I'm not that well prepared either. But I think the best thing to do actually instead, let's just look at, our past results and let's go to homework 6 and let's see where we actually did here. Okay. So what
You know
is
what they
this?
say,
So
past results are the best indication of future performance.
yes, sir, that's it.
Ah, yes.
Got to get that Baker lore in there.
Yes, sir. Okay, what do we got here? So I think you know what? Let's just do homework 7.9. Honestly, again, why not? Let's just do that. Let's just rework it from scratch. Yeah.
Wait. Homework 7.9? Are we not doing 7.1?
Because I'm just gonna be winging my way through explaining how to do it. I think a good refresher on like 7.9 because it's similar. I think this is a good to do.
So 7.1.
Oh, I
That's
found it.
Yeah.
Okay, cool.
but
Which example problem did he go over exactly for that?
Example 7.1. Let's see. 7.2. He went over a couple actually. 7.1,
you went over
7.2.
yeah.
Yeah, I
Yeah.
He
remember.
went over 7.1, 7.2, 7.7. Let
All
me
right.
see.
So basically,
Oh,
what do we know?
sorry.
Nothing.
All right. So what do we have? So example 7. You know what? Forget it. Let's do example 7.1. We need to
Okay.
actually know what we're doing. Okay, we're doing 7.1. I don't care. Okay. We
Yes,
have
sir.
let's see. So we have a conducting triangular loop carrying a current of 10 amps. Find H at this point due to one side of the loop, or side one of the loop. Okay, let's just draw it out then, I guess. Sure. Let's see what we got. We have X, Y. We have 1, 2. It's one on top. This is your thing right here. Draw your triangle. Yes, awesome. Which way we're going? We're going this way.
One moment. I'm gonna join from my computer.
For sure. So we got this, and then this is a 10 amps right here. All right, this is side 1, 2, 3. 1, 2, 3. All right. What's going on here? Okay, so we are given the following. The conducting triangle in figure 7.6a carries a current of 10 amps. Find H at 0, 0, 5 due to side 1 of the loop. What is side 1 of the loop? I have no idea.
Well,
Yeah,
side one of the loop is the side one that you just labeled.
yeah, there you go. All right. And they draw figure 7.6b, which looks like this, where you have your side 1 of the loop, and it's going this way.
Mm-hmm.
And you have like the point 0, 0, 5 due to side 1 of the loop. So we're just purely looking at side 1. So I'm using a different color here. This is alpha 2 and alpha 1. So this is alpha 1 right here, 90 degrees, and this is alpha 2.
Okay, so how do we determine which is alpha 1 and alpha 2?
That's a good question.
Oh, they see right there, alpha 2.
Let's see. And I'm also need to label, let's see, we need to label a length and a row. So this is your row essentially. And this is your a row vector right here pointing in this direction.
Mm-hmm.
And then you have your a length. Yeah, a length is going this way. Nice. X and Z. Okay. So yeah, so basically this is X, Y, Z. Yeah, so what does this look like essentially? So if we were, I'm just going to draw a 3D representation of this really quick, just to kind of make sure I get both of these in there together. So this is your X. Hold on. What is this? All right. This is X, Y, Z. So we have our X is 1, 2. And then you have your Y is 1. And then you basically have something like this. That's your triangle going this way. And it's, yep, it's in that direction. And then your points are here. 5. And this is where you want your H point to be. This is our H point. So you want H at 0, 0, 5. Awesome. All right, so problem is set up. So now what do we do? To determine, all right, well, what is the formula that's given to us so far? So if the conductor, so we're given essentially a finite length essentially of the conductor, which it looks like. So I wonder what that means though. So I think it's because we're basically going from point A to point B. So this is like your finite length essentially. And so we're gonna have to use this formula. This is the way I understand it. Let's see, 1/4 pi rho. Let's see, times cosine alpha 2 minus cosine alpha 1. A theta. Or, yeah, this is, no, A phi, my bad, it's A phi. And this is rho theta, no, this is rho phi z. So we're basically using cylindrical coordinates, I believe. Rho phi z, right? Yeah, this is cylindrical. I don't know how much that'll help us, but it will, most likely. Okay, so, all right. So your A phi essentially is basically your A row, oh no, your A length cross your A row. That's given in the book. So that's where we're going to come up with your A row essentially. And this is also why we have these labeled. So we have an idea. So essentially, A row, or A phi, I mean, is your length. So length is going in the X direction, cross AZ, which that's in the row direction. And X cross Z, I'm just going to do the right hand rule really quick. that equals negative y. So that's going to be our a row. So, or a phi. I mean, I keep saying a row.
Okay, how did you get from a length times a phi to? Oh, never mind. Okay, sorry.
Now you good.
Okay.
So basically, your a row. So the row is basically, I think that's like your height when it comes to your pole, or like your finite length right here. So we're looking at this length of this pole, and we're basically starting from like our current like triangle to a specific point, and so that is basically your row direction. Now, when it comes to a length, I wonder what that is. So is that basically due to side one of the current? So your AL is the line current. So that's basically the direction of the current. So whatever direction your current's flowing in, that's going to be your AL. So I'll just make the note over here. So AL is direction of line current, and your A row is the direction.
Oh, I
Let me,
see. I know why it's a negative AY, because when you do the right hand rule, you're basically, if you're doing the cross product, when you have AX, it's pointed to have your fingers point towards you, and then whatever the Z direction is pointing up, you want to have your palm pointing uh, at the top, basically, and then you just curl your finger, and then you're just left with your thumb pointing in the negative Y direction.
What?
Okay, let me explain it this way.
so
Okay.
I could
Yeah,
draw it
I
if
got.
you want.
Yeah,
I was thinking like because you're pointing in the direction of X, right? And then your fingers are coming out of the screen towards you, right?
yeah. Okay, so I'll put this. So AX is your fingers, AZ is your palm, right? So given the direction of AL pointing in the positive X direction, X is coming towards you, so you have your fingers pointed towards your body, right?
Mm-hmm.
Then we see that AP is going in the same direction in the Z direction, and so since it's going up, your palm is pointing upwards. You know, it's directed upwards. So it's kind of like I have a camera. Why don't I just do it this way? Oh, this would be a little bit awkward about the orientation.
You could, or I could draw it really quick if you want.
Let me see. So like I have my fingers pointed at me, right?
Mm-hmm.
And then I have my Z, right? Think of Z as up here. I have
I
my
can't.
palm
I
like
can't
this.
see it. Yet. Second.
Oh wait, Michael's recording. Yeah,
Oh, sorry. You want me to stop sharing real quick?
yeah,
All right, I'll stop sharing. Hold on.
yeah. Basically, think of it this way. So boom, you have your fingers pointing towards you, right? So this is towards me. So if you do it to yourself, it's in the X direction, the positive X direction. Then let's say Z is pointed up here, right? So I have my palm pointing up this way, so you can see it. Boom.
Here, why don't you flip the camera and then you show us like a first person view instead?
Yeah, let me do that. So you see this is my hand.
Uh-huh.
So pointing towards you, boom, and the Z is in this direction. So I have trying to make it as straight as possible, but yeah, that's my Z direction is pointing up. Then to get the Y direction, you just curl your fingers into your palm as always, and then whatever your thumb is left at, which is right here, think of that as on the negative Y direction.
Wait, I thought that we were supposed to point our thumb towards the direction of the current.
There's
No,
different ways of doing the right hand rule. Me and Will just use that way.
yeah, because
Oh.
I learned it from Manny. That's how he helped me out. That was like a long time ago. But the reason why, if you even questioning like why did I use AX for my fingers, is the way that they wrote out the equation. So remember Michael, he put like AX cross product with a Z.
Mm-hmm.
since he had AX first, I used my fingers. Now,
Oh.
if it AY first, then I would use my fingers for the AY. So then this direction with my fingers would have been pointing this way.
For the negative AY, I just the way I do it is for you have AX and AZ, right? It's AX cross AZ, right?
Yeah.
Well, the thing is that I think of it like XYZ, like just a repeating pattern, like XYZ, XYZ. And if
Mhm.
like you have X crossed Y, you get positive Z. If you have do Y crossed Z, you get positive X. If you do Z cross Y, you get or Z cross X, you get positive Y.
Yeah, you
So
do it.
as long as it goes forward in the direction of that infinite repeating pattern, then you get a positive number. If you go backwards, then you get a negative number.
Yeah.
So like Z cross Y is negative X, or
Yeah.
Y cross, yeah, you get the point.
You said Y crossed Z or X.
What?
What were you trying to say at the last sentence?
I
was
said Z cross Y would be negative X.
okay, let me see if I do that. So Z cross Y, so boom. It would be negative X, right?
Yeah.
Oh yeah, boom. So I have my fingers pointed in the Z direction, and I have my palm pointing at the Y direction right here. Boom. What does it do? Negative X right here is pointing outwards.
Okay, let's continue then.
Yep.
Alrighty. Let me share the screen. Yeah, if you guys want to like review like right hand rules, so like just to make sure like you're comfortable with like a certain method.
Are y'all comfortable of how they got cosine A2?
Alpha 2, you mean?
Yeah, alpha 2, my bad.
So
I want
alpha.
to.
What would you
Huh?
say?
Oh no, go ahead, Tom.
No, I don't know. That's what I was gonna say.
Yeah.
Yeah, I got you. So do you have Michael, can you pull up your you already have streaming.
Yeah. I'm
Okay,
streaming.
boom. See where Michael has alpha 2, right? And you're
Mhm.
just trying to find the cosine of that. You pretty much just do SOHCAHTOA, what I understood. So you see on the adjacent side, you see the length is 2, right? That's how big it is.
Mhm.
And then since we want to do the hypotenuse next, we do 2 squared plus 5 squared, and we do the square root of that. So we get 4 plus 25 equals 29 square root.
Mhm.
And that's how they got alpha 2.
Oh, I
What?
see. I see how. I think Will Thomas was asking like, why is Alpha 2 here versus not over here, and like why is this Alpha 1? Why is this Alpha 2? Is that what you're asking?
Is that what you're asking, Thomas?
I don't even know.
What were you asking?
I don't know what you were trying to explain.
Okay.
Oh, okay. What I was trying
He
to
was trying to
explain?
give you the value of alpha 2, I think.
Yeah. I was trying to give you the value of alpha 2, where it came from.
Oh
Hmm.
well. If you want, I could explain like where Alpha 1, Alpha 2 come from. So basically, you have your point, right? Like your point of interest,
Mhm.
I'm sorry to cut you off, really quick.
for
In
sure.
the book, did they give us the side one figure? Like,
Yeah,
Mhm.
okay, so we didn't have to derive that. Okay.
the side
Yeah,
one figure
no.
is
It's
this figure
given.
right here.
Okay, they just give that to us. Okay, cool.
Yeah, that's given.
Okay, that makes everything
Better
easier.
be given in the exam.
Well, I don't think it's going to be given on the exam.
Well, if they tell us 0, 0, 5 and they give us an XY plane, then they're probably going to want us to like figure out the Z and
No,
draw.
as long as they give us the figures, that's all I care about, because I can actually know how they got those values. I know
Okay.
we have to find alpha 2 and alpha 1. I get that, but just by looking at the pictures, I can figure that out. But if we weren't given the pictures, oh no, I don't know.
No, for sure, for sure.
Yeah.
All right, so let's just continue with this then. So basically, where's Alpha 1 and Alpha 2? If that's not given to us, how will we find it? Well, first of all, let's see. So we have our line current right here, right? This is our line current. It's
Yeah.
going in this direction. This is the direction it's going to. So let's say you have your field point right here, and you want to basically start, like imagine like you take like a compass, for example, right? and you're basically putting your needle here, and then you're putting your pencil here, and then like you have a straight line here. So this is 90 degrees. So that's alpha 1 right there. So this is your alpha 1. This is like the first angle that it makes with like the thing. And now
Oh.
rotate your compass this way to where now the line is going to be over here, because you're going in the direction of your current. And so now you end at alpha 2. Okay, I just want to make sure, because I see that in the book now. It's starting to make sense, like how they derive the alpha 1, alpha 2, where that comes
Wait,
from.
you
So,
ended alpha 2? What do you mean? Like, I don't know what you
I
mean by
see.
rotate the compass.
so that's where like alpha 1 and alpha 2 come from. Because like, let's say for example, they just give us like this.
Hmm.
Like, how would we know which is alpha 1, which is alpha 2 when using this equation?
Oh, that seems sick. Okay. Draw a compass, Michael. Like draw
Wait,
a
wait, hold
compass
on. Can you do
with
that again for me? I
the
kind of
tip
got
and the
lost.
left.
Sorry.
Nah, for sure, for sure. So like, let's say so this is the direction of our current, right?
Yeah, yeah, yeah.
So to go to our starting point, so we have to start over here on the left, and then the current's gonna boom fly this way. So let's go to our field point, our point of interest, 0, 0, 5.
All
Let's
right.
put the needle of our compass right here, like the needle,
Oh, okay.
and let's put our pencil over here or something like that. And then you draw a straight
Wait, where's
line,
over here?
right here.
Okay.
So this is the needle. This is like the lead. Hold on, I spelled lead wrong. There you
LED.
go. Yeah.
Mhm.
Let's see. Yeah. So basically, that's that, and then you just look at the angle that it makes with the axis.
Okay.
90 degrees. So that's alpha 1. Whatever, or it could be any angle. It doesn't matter. Like, let's say for example, the current is let's say the current's like all the way over here.
So alpha 1's the intersection between the 2 points.
Pretty much, yeah. That's the angle. So, but like, let's say, what if the angle is like, what if the line current's like this long and the point's over here? So, what would alpha 1 be? Well, we'd have to look at where the current's flowing. So, it's flowing from here to here. So, we know that where it starts, that's going to be alpha 1, and where it ends, that's going to be alpha 2.
Oh, okay. So it's flowing to the right. Okay, so where it starts to where it ends.
Yeah, so the alpha 1's always going to be your first angle. And then as the line current flows, so now you're going to be here, here, here until you get to here. And this is where it ends. Boom. What's the angle? That's alpha 2.
Okay.
Let's see. I just want to make sure though, is alpha 1? Because if we had it extended like that, yeah, so alpha 1 would be, it looks like alpha 1 would be this guy. So this would be alpha 1.
Oh, the outer one?
Yeah. I'm looking based on the book. If you look at figure 7.5 in the textbook, figure 7.5, that's in page 301.
Hmm.
That's what I'm using right now to check.
Okay.
Okay, yes, yes.
I don't know though. Maybe it's the small. Maybe they're supposed to be acute angles. They're not supposed to be obtuse at all. It's all supposed to be acute. Who knows? But anyway, all right. Enough time with that. But
Let's
anyway,
just deal with it with let's just deal with the cute.
we're given it anyway. It's a right angle. This is yet to be solved. So let's see. Cosine of alpha. So what is rho? Rho is 5. That's given to us. What's the
This
length
plug
over
and
here?
chug here, basically.
Essentially, yeah. What's this length right here? 2. Or basically, hold on, let me just redraw this triangle. So this is the triangle. This is alpha 2. We know alpha 1. Alpha 1 is 90. This is known. Alpha
Mhm.
1 could be easily derived. What's alpha 2? Well, we know this is 5. We know this is 2. What's an equation that can help us find alpha 2? Well, this is adjacent. This is opposite. And so what's that going to be? Going to be, yes, sir. 10 alpha
You gotta
2.
figure out the hypotenuse
Wait,
first,
cosine,
right?
right?
That's gonna be for when we use this. But first, we
Oh,
actually have to figure out what the
well,
angle is.
Okay.
like
So I'm
opposite
just
over
basically,
adjacent.
Wait, do
yeah.
we need to find out the angle if we just need to find that use that equation?
Uh, well, I don't know what to plug in for alpha 2 though. I
No,
can
you
plug in
don't need to
alpha
plug
1.
in anything for alpha 2 because if you do SOHCAHTOA, cosine is adjacent
Yeah.
over hypotenuse. So
Uh-huh.
you just find the hypotenuse, which is the adjacent, which is 5 squared plus 2 squared, the square root of that.
Is it tangent of
Oh, I
opposite?
see what you mean.
So that'd be 20 square root of 29, which is
Yeah, this is
adjacent
what.
over hypotenuse 2 over the square root of 29. That's what Will was talking about earlier.
Yeah.
True. Okay, I see what you mean. Okay. Good. Yeah, so there's no need to actually solve for the angle if you actually know what it is. Okay, yeah, true.
Mhm.
So 25 plus 29 squared root of 29. Yeah, that's true. Yeah, so basically you could just plug in, yeah, so cosine alpha 2, that's just literally, that's adjacent over hypotenuse, right?
Yep.
Yeah.
2 over that. Yeah, there you go.
I don't know why my geometry teacher drilled that in me. Thankfully.
Saying,
No, that's good. Yeah, so yeah, you could do it this way. There's also, I think, like if you were to like do like this, like if you were to do like 5/2 and then like you do like tan inverse to get alpha 2, um, and then you actually get a value for alpha 2 and then you plug it in to here, you should get like this as your answer. But you know what? Let's just stick with your guys' way. It's better.
Yeah.
Mhm.
Okay. So now I guess
Wait, I just realized we can just probably put all these examples on our cheat sheet.
yeah,
that's
bro.
probably,
Yes, that's a good
that's
I'm
a good.
idea.
definitely.
We just gotta understand them.
Yeah. Well,
Yeah,
we're
so
understanding them now because Michael is here to teach us.
Yes, sir. Yes,
Isn't that right, Michael?
I'm
We also have to
Teaching
account
is
for
fun.
whatever thing he may ask that's different from his examples that he provided.
Hmm.
Like any numbers that change or whatever like it asks for, even with
So
the
yeah, for
like
7.1, he just threw that on the board. Like the one that we're doing right now, that's what he was explaining.
yeah.
yeah, this
So
is like
we're good right now. For
Mhm.
I have a quick
7.2,
question.
didn't do it.
Sorry, there's like under where you said cosine of a2 and you said 2 over what is that, square root of 29?
uh-huh.
How'd you get square root of 29?
So this is
Pythagorean theorem.
Oh,
yeah.
that's hypotenuse? Or,
Yeah.
Yeah.
okay.
Yeah, I forgot the right angle.
Just
The magnitude. Yes.
Yes, sir. So
Yes.
cosine of 90 is
so then
let's go.
and then you would just plug in cosine alpha 2 minus cosine alpha 1 times 1 over 4 pi rho, and that's it.
I think so. But before we do that, let me
Oh, I
ask
see
you
where you're
this.
going with that. Okay. That's
Oh
for
yeah, that is
each
it.
one.
Okay, cool.
Okay.
So we
Yeah,
have
because
to
then cosine of 90 is just 0.
Yep.
yeah,
Cool.
Yeah.
awesome.
Okay.
So 7.7 next.
Yes, sir.
Yep, that's pretty much that. And
Yes,
then let's
sir.
just make sure that okay, so I'm just gonna make sure we know what we're doing here. So yeah, so basically, like the book says, we're basically plugging in I, which is 10 milliamps or 10 amps. I'm sorry. So that's 10 over 4 pi times what's rho? Rho is 5. And then you got your cosine values. So that's 2 over square root of 29 minus 0. So just leave that there. I'll put minus 0. Why not? Let's be explicit. Times what's the
Whoa.
AV? That's there you go. Awesome. There you go. And yeah, that's what the book says as well. So okay, we know how to do this problem. Example
Nice.
7.2.
Yes. Who's down to do a PDF of all the problems that we're going over and just throw it in a sheet of paper?
Hey, man.
Do you have time to do that for us, Carlos?
All right, sure, I'll do it.
I'll bring my own cheat sheet just in case, but Carlos can make like a copy of all of that for us. I'll be helpful.
I got you. I got you. Okay. Yeah, bro, like I was telling Michael, like in the car because we carpool, right? I was like, bro, why didn't I put all of the tests from the beginning of the semester until test number 6 on the 2 sheets of paper?
Because
I
you
saw someone
think
do that
after.
for the exam that we just took.
What was what was that?
Yeah, I think she just put like every single test question and then printed it into the paper that she got.
Yeah. Yeah, that's what's it called? That's what I was thinking of doing, but the idea came when I was already at UNLV 10 minutes before the test. I'm like, bruh.
I would have done it, but I didn't have the means for it.
Nah, bro. Like he said, it's a cheat sheet. I'm like, okay, cool. And I still failed. But
Yeah.
I don't care.
It's
We
okay.
still failed with the pages.
I'm so
It's
mad.
okay. You have to aim for 50 to pass. Is that what I understood from that?
He said that if you
Yeah.
get, as long as you get above the average or above 50, you'll pass. So
Oh, okay.
Yeah.
Well,
Yeah, I did the calculations. I got a 54, bro, so I'm good.
wait, what are you talking about?
Like the
you already got your
average, like
final grade?
I
Oh,
calculate
okay.
I calculated all of my exams. I calculated the math lab, the homework 0%. I didn't do nothing on that, and all added up together, it got me a 54. So I'm good.
You should.
Awesome.
Yeah, but can rely on that next semester. All right, cool. Yeah, while
You
you guys
guys
are
want?
going over these, I'll do the PDF.
All right, if you want, for sure.
Awesome.
Thank you.
Yeah, let's just start 7.2 times running.
All right, so we got, let's see, so let's do 7.2, 7.7, 8.4, 9.4, and the rest we could just do on our own.
Dude, I can't believe I'm actually doing this.
Yeah, sounds good.
Mm-hmm.
All right, let's do it then. All right, so what is 7.2? 7.2 looks a little more complicated. Uh, let's see, find H at this due to the current filament shown below. What is the current filament shown below? What is this creature? Uh,
It's a
I don't,
7.2 example?
yep, example 7.2.
Wait, did
What
you
is
say we
this
had
creature?
that was one of them?
Yeah, that
Oh,
was
okay.
one.
Oh, I thought it was
How good are your
7.7.
guys' eyesight?
It's
I don't,
terrible.
I don't think he would put something like this on the exam.
Okay, maybe I misread. Maybe it's section 7.2, example 7.1.
Well, yeah. Well, I see the board and it says 7.7.
Okay, let's do 7.7. Yeah, let's just
Like,
skip.
Yeah,
It's just written weird.
7.2. Yo, no, yeah,
7.7,
that's
the
bad.
section or
oh,
the
that's
example?
7.7. Oh shit! I thought that was
Yeah, the
7.2.
Yeah,
A
no.
equals minus
I
His handwriting's a
square
little.
divided by 4.
oh that is
You
actually
see the line through the
Yeah,
7?
example 7.7.
yeah.
Oh, so example 7.7. Okay, so all right, so basically know your basic Bayards of art law, like just know your this thing and you're good for chapter 7 for the most part when doing Bayards of art. You got this guy, which we're good, and then Smith chart. All right. So now we're gonna do this example is basically the magnetic scalar and vector potentials. So it's basically yeah, we're doing potentials now, which is nice.
That's potentially alarming.
Mhm.
Uh-huh. Uh,
And then I'll just note here this is a Bayards of art law.
So the Bayards of art law, is that mostly the 1 over 4 pi rho cosine alpha 2 minus cosine alpha 1?
That's like your general formula for like a finite pole. Yeah.
Okay, cool.
Bayards of art law is like this crossed with this over something else. I don't want to learn that. I think this is reasonable because it's already derived for us, and that's what he probably put on there. Yeah.
Mhm.
All right. All right. So there's two ways of solving this, and I think he wants us to know both ways just in case. So we are given a magnetic scalar potential. Well, I think the first thing we should do is write all the formulas we should probably know. So we should know first of all. All right, so formulas. Let's see. So we know H. Let's see, is equal to the negative gradient of the uh, magnetic scalar potential. Let's see. So this is the magnetic scalar, oops, scalar potential. Awesome. All right, so that's that. And this is if j equals 0. I would just put that there. Why not? If j equals 0. Okay, nice. Let me write that a little better, actually. If J equals 0. So that's the first formula that's boxed, and then so A. Well, actually, I'm gonna just say this: B equals the divergence of A, or that's basically the gradient cross, or not the yeah. It's the del operator crossed with the A. And what is A, you might ask? Well, A,
Apple.
that too.
I was gonna say avocado, but that works too.
I learned that in kindergarten.
So A is what's given, right?
We're about to find out when we do the problem. I know for sure one of them should be given.
No, yeah,
Let's
A is given.
Oh yeah,
magnetic,
I see it. I seen it.
magnetic vector
Magnetic vector
potential.
potential.
Yes.
Yes. And then B is like your B is the magnetic flux essentially. Flux density, I should say. Yeah. So that's that. And is anything else we should know? No, A is just your typical Pirates of Heart stuff, and all right. And then the last thing we should know is the flux or the net outward flux is equal to the closed line integral of A dot L or A dot DL. That
I
is
think
the last thing we need to know. Okay, so I think we can go ahead and start example 7.7. So I'll just box this here.
For sure.
All right. Those are the three formulas we need. 1, 2, 3. And then I'll just separate them so we don't confuse them later. All right. Oh yeah, this is the
thanks, Unc.
Don't say that, bro.
network flux. All
Oh,
right, so
area.
we're given A. Let's see. So A is negative rho squared over 4. Let's see. AZ. Calculate the total magnetic flux crossing the surface. Boo, boo, boo. So, all right. So, given this Webers per meter, it wants us basically to find B. That's what basically magnetic flux means. Total magnetic flux crossing the surface. Crossing surface. And the surface is basically enclosed by phi equaling pi over 2.
I wonder how they got that.
How they got what?
It's given to you.
Oh,
Oh my.
ChatGPT's back, by the way.
Oh,
Oh, okay, let's go. Let's go.
Wait, what?
ChatGPT's back.
ChatGPT.
Oh, it's back?
Yes. From the.
Yeah.
I'm sorry. I'm sorry. I said.
Good. Why don't you ask it to verify everything that I'm doing so make sure like I'm not just renting, nonsense.
I'm just
Nah,
gonna
bro, you're
ask it.
good.
I'm
Keep
gonna
going.
ask the O1 model to freaking explain the.
One model for the win for us to get through Smith charts. Nah, I'm just kidding. It cannot do graphs yet, I think.
I
Okay,
wish.
what do we have here?
I can't wait till we have artificial general intelligence that can take my job and kill me.
General
Uh,
intelligence?
Yeah. I can't wait
yeah,
for
what
artificial
Nvidia's
general
doing.
intelligence to just kill me.
All right, let's see what we got here. All right, so basically, what do we need to do for B? B is essential. So how to find B is essentially do the divergence of A. What is the divergence of A? I think that's just a formula that we're just gonna have, honestly. If you go to, I think I have it in my formula sheet.
I love formulas.
Let's see.
Bro.
Where's the formula sheet? I know the
Ravioli,
answer is like
ravioli, give me the formuoli.
where's it? I forgot. It's Wednesday, so we close an hour earlier.
What are you talking about?
You guys don't get the reference? Okay, fine.
That's why you
Bro, my neighbor showed me Unk on TikTok. I'm like, what the heck? Or is that the one that you're talking about or no?
No, it's just a way to call people old.
Oh, Unk. Oh, never mind. Don't search up Unk on TikTok, man.
wait, y'all, wait, y'all didn't know?
Don't search him up. Don't search him up.
Yeah, where you don't search up Uncle Ruckus. You don't want to do that.
Alright.
Yeah, you know what? I'm just gonna trust that's it, and let's just say okay. We know that B equals
Yeah,
thing
you were trying to
cross
find out
A.
the cross product. How do they do that cross product, huh? You trying to
I'm
figure that?
actually trying to understand this as best as I can.
Yeah,
How?
let's just do method 2.
Do you want me to just
Yeah, I
send
think
you the
method 2 is the one.
1 second.
Method 2?
Yeah, let's
Alright.
see what we can tackle that we do know we comfortable with.
Yeah.
Well, method 1 would be pretty easy if I just had the formula for the cross product, but oh well.
Oh
Yeah.
yeah, 1 second. Let me just paste the formula for the cross product.
Yeah,
Oh
yeah.
yeah, for sure.
I have that in my last one, my last formula sheet. Hold on. Is this my formula sheet? Where's my formula sheet?
I just got to figure out how to do that. Simon, pretty fast. What was the? I'm gonna have to go back.
No,
What chapter was that again with the cross product?
I
Three.
It
don't
was
know.
either chapter 1 or chapter 2. I
I feel
think
like
it's
it was
chapter 1.
one.
What the gradient is different. If I
Chapter 3, I think.
Yeah, so A
The Dell operator is chapter.
DPEZ.
Yep.
D no,
Hey,
that's the row
It's
DC.
much easier to memorize it in matrix form, the cross product.
yeah,
It
Because then
honestly.
after if you memorize the whole process with
Bro.
it, you can do the
Oh,
cross product like that.
wait, how did
I think
I?
it's so
Where?
much like finding a determinant, the process.
All right. So are we gonna stick with method 1 or 2 so I can throw it in the Word document?
I think we should just try both because they'll either way. I think it'll be nice.
yeah.
Okay.
Because method 1 will be really easy if we just know the formula for the cross product. That's just it. As soon as that's just plug and chug.
True.
Oh yeah. I found the formula. Let me just throw this in the general chat so everybody can see.
Yeah, please, thank you.
Yeah. See, I help. I smart.
Yeah, for real.
Boom, right here. Just an example. Oh, Thomas. At the same time, thanks, Thomas.
Wait, actually, do I have Del Crosse in there? Yeah, there we go.
Can we like just never mind.
Okay, I see. All right, I see what's going on here. Okay, so we're taking the thing with respect to row. Yeah. So let's see, because there's only a row over here. So the only thing we could really take the derivative with respect to is row when we do this. So you're given this entire like band of like all these. There's 6 different partial derivatives here, but which one?
Yeah. Then you
So
can
how
just do a little mental math in your head, like make it make sense.
I'm gonna see how the let's see why does the book choose this one? So the book chooses AZ thing row thing, yeah. Okay. With respect to row, because why is this one not used? Because
Oh, wait. This is in cylindrical coordinates, right?
this is cylindrical coordinates, yes.
You're using the wrong one then.
Yeah, just
Let me go the right one. I mean, Thomas has everything there, but let me just.
no. I also see cylindrical in here too.
Okay.
Yeah, I see them.
Oh yeah, I'll throw it right here just for my sake, because I want to learn it too. Okay, shorty in here.
You know what? Let's just write the whole thing out. Honestly, I'm just gonna write the whole thing, and then we'll just go ahead and we'll simplify after that. Because I actually want to understand this. Uh, all right, come on, come on, come on, come on, come on, come on.
Man, I guess I lost my sheet, my formula sheet, my last one.
Ooh, damn.
My formula
I-
sheet from the last exam is very. Minus this. Okay, that was a bit tedious. I'm sorry, but let's go at it now. Okay, so we have this guy right here, right? We have this guy. So if you want to take if this is in terms of AZ, you do cross product. Anything with AZ is just probably going to be canceled out, right? Can I say that? So like if this is an AZ and if I have AZ terms over here, it'll all just cancel.
Yeah.
1 second. So it's
Well, I look at it this way. You see,
no, actually, wait 1 second.
I got you.
Continue. Sorry, continue. I'm an idiot.
Oh no, you're good. Okay, so if we look at the given formula A, right, and we see that it only has rho in it, correct? It has the P.
Uh-huh.
If we look at the subscripts for each case, we see okay, the one that you crossed out, that's going to be gone away, because if you try to take the partial derivative with respect to wait, hold on, I think I might be an idiot too, but oh no, I'm good, because in the subscript where they have A right there, but it has like phi in there. We don't have anything that has relating anything that has phi in there, so that goes to 0. The subscript for AP in here, it only has
Row. It's row.
Oh no,
oh
yeah.
Yeah,
Yeah,
no.
I
I see what you're saying, but basically the
oh my bad.
DAZ D phi goes away because there's no phi term. DA phi goes away because there's no phi term.
this
Or
is
Yeah,
phi
by
doesn't exist.
this is by there's no
Yeah.
Z. We're taking with
That's the only
respect to
one that
Z.
survives. Yeah.
Yeah,
Yeah,
that
this is
one's
the
the
only
only
one
one that
that
survives.
survives.
Yeah.
yeah.
Because
I,
this
I
is
okay.
yeah.
I understand it now.
Yeah, because we take with respect to theta, there's no
Yeah.
theta here, no z, no theta.
AZ.
There's is with respect to rho, but this
So you
is
just got
also AZ,
scripts
so that's
and
why.
bottom
So
derivative.
that's why you would. Oh, okay.
Okay, I think that makes sense. So you got to look at the subscripts for them and the partial derivatives. So we have rho in here, but the subscript is phi. So and we don't have no phi, so that's 0, so that goes away. We have the subscript AP in there, which we have P in our A thing, but it's doing the derivative with respect to phi, and we don't have phi in there, so that goes away. Okay.
Yeah.
Okay, so make this short. So you see phi. Okay, okay, that makes sense. Okay.
So B now essentially is just left with this guy. So we have this. This is the only surviving term because this is the only one that's with respect to rho is these two. And this one, from my
Yeah.
understanding, is with AZ, and AZ is here. So AZ cross AZ is 0, so that's why I crossed
Yeah.
that out as well.
Mm.
That's how I understand it. But if you guys find another explanation to this that's more logical, you could ask ChatGPT since it's working now.
Yeah, true.
But for now, I'll just keep working this out while you guys look for an answer if you want. But yeah,
Control of magnetic
uh,
fields on the
we also
momentum.
see this. It's a surface, and phi is constant. What does that mean? It means that essentially you have a cylinder. Here's like your let's see. So here's your row, and your row is essentially, so basically it's like multiple cylinders out here. So you have like a big cylinder and a small cylinder, and then you have like the area shaded in between. But it's also just a surface. So it's essentially just so we have like pi over 2 here, and then this is like your row. Your row is essentially from 1 to, your row is from 1 to 2. So let's say this is row and this is z. So 1 to 2, and then your z is from 0 to 5, and this is your surface. Because phi is constant, because like I could be taking this rectangle and like rotating it like all the way around, but it's just constant at pi over 2, so I could just basically write it as a rectangle. And so what does that mean? It means that we have essentially a ds that's in the d phi direction. And so what we have to do now is for our ds, we need to go ahead and find the surface area integral, or the surface area thing that would have a phi as our constant, and that one, and it's also in cylindrical coordinates, and that happens to be uh, d rho dz. And so that's basically what we have there. And that's where the book gets that as well. I see that. Now I'm also trying to oh yeah, and now also we should probably go ahead and take the derivative of this guy. So b is essentially, if you take the derivative of this would be, you have your negative, so you have, with respect to rho, it's just negative 2 rho over 4. Yeah, a phi, and this would essentially be negatives cancel, it's just rho over 2 a phi. All right, so this is our b, and this is our little integration thing. See if that makes sense so far. Yep, it does. So we have to find the total magnetic flux. So this is so we found the flux density. So this is the flux density.
Wait, okay, so sorry, can you just please just real quick go over never mind, I'm an idiot. Rho is from 1 to 2 and z is from 0 to 5, which is why you get the bounds. Okay, never mind.
Oh no, for sure. And then phi's constant. So
Yeah.
it's such a
And
sheet basically.
what does the pi over 2 have to do with it? The phi?
That's just basically a constant. So like you have a cylinder. Let's see, here's your cylinder. And then I like rotate like pi over 2, like I start at 0, and then pi over 2 happens to be over here.
Oh,
and then I'm just taking the sheet basically, like this rectangle.
So just that portion, like that infinitesimally small portion.
Yes.
Or thin. Yeah, okay, cool.
And this actually makes sense that we're integrating from with d rho dz as our variables, because that's the thing that's changing. But I first identified what direction my ds vector is pointing in, and it's pointing in the d phi direction. And so that's why I chose this, because this is a formula basically. Okay, so now with this in mind, well, all we need to do now is basically find the flux. And what is the flux? Okay, so we also have another formula. I should probably write here. This is equal to that's also a formula that's equal to that. So there you go. All right, so all we need to do now is essentially plug and chug. So we have our integral. We're going, let's see, we have rho over 2 a phi times, or dot product, your ds, which is d rho dz a phi dot a phi, that's just 1. Oh yeah, and also we're doing d rho first, so we'll put the rho constants here. Oh, what's rho? Rho is actually 1 to 2, my bad. 1 to 2, and then z is 0 to 5. And so we could take the 1/2 out as well. So that's just going to be, let's see, rho, d rho, 1 to 2, 0 to 5, db dz, or d rho dz, whatever. So it's just basically evaluating the integral. So that's going to be rho squared over 2 from 1 to 2. And then this is your dz. So if you evaluate that, that's going to be 4 over 2, which is 2 minus 1/2. So 2 minus 1/2, that's 3/2, right? So let's see, 3/2. 3/2 dz, which is just basically, if you evaluate this, you got 1/2 times 3 over 2 times 5, which is basically 15 over 2 times 1/2, or 15 over 4. And is that what the book got? Yes, because they got 3.75 Webers. Answer. That's it. So that's method 1.
All right, cool. Me too.
All right, Michael, are you able to zoom out real quick?
Sure.